Today, I'm going to be making a presentation on the remobilization and adsorption of gold on colloidal chlorite at the Hardrock Orogenic Gold Deposit, Geraldton, Ontario. This project was made in collaboration with an NSERC grant together with Greenstone Gold Mines and the University of Ottawa. My name is Jordan Harris, and my associate professor on this project was Olivier Nadeau. Starting off, I want to just introduce the field area. The field area was located in Geraldton, Ontario. This area is located 200 kilometers northeast of the city of Thunder Bay. Geology-wise, this is at the contact of the eastern Wabigoon and Quinteco subprovinces. And there is a total estimate of 4.2 million ounces of potential gold at this mine site. Mineralization. There's two types of mineralization that are occurring at this specific orogenic gold deposit. The first is quartz carbonate stringers, which are a network of stringers that are primarily narrow and have been folded due to structural constraints. These network of stringers are narrow and have been Sulfide replacement is the second type of mineralization that is occurring. This is at an interaction between the iron-rich formations, which have allowed for different chemical reactions to occur. This allows for large replacement of the iron oxides with sulfides. The resulting processes is sulfide lenses around the iron formations. This is allowing for oxide minerals, primarily magnetite, to be replaced with pyrite and pyrrhotite together with disseminated gold. Fieldwork. For the samples collected at the mine site, different drill core analyses were picked. 1 to 2 kilograms of each sample was collected. Samples were determined to be in different lithologies based on the drill core analysis completed by the mine site. The 5 different lithologies studied were greywacke, gabbro, iron formation, which included the biffs, porphyry, and quartz carbonate veins. Each of the samples were heavily altered by chloritization, ceratization, biotization, albertization, carbonatization, silicification, hematization, and sulfidation. Samples were collected at different depths and different amounts of gold content. Now looking at the petrography of the samples. Optical microscope photomicrographs were shown of the different types of main lithologies. Starting off, we're looking at the gabbro and the greywacke. In the gabbro, we can see that it is heavily altered with different amounts of albertization, chloritization, silicification, and hematization. It is found that the chlorite is forming after the biotite and is allowing for the chloritization reaction to occur. In the greywacke, we can see this presence of alteration, including ceratization, carbonatization, and hematization. This is occurring around the detrital plagioclase quartz matrix. Next is the greywacke and the biff. As we can see, we are looking at a strongly altered greywacke with different amounts of albertization, carbonatization, hematization. In the biff, we are seeing the alternating layers of the sulfides and as well as the silicates. In the biff, we can see different alterizations, including hematization, chloritization, and carbonatization. Finally, we're looking at the last two, which are the different porphyry rocks. In this example, we're looking at the quartz feldspar porphyry and the quartz veining. Now the methodology. The methodology first starts off by analyzing what's the different types of lithologies. This is split up into the 5 different lithologies that I just went through in the petrography. We want to separate these different lithologies into the different clay-sized particles to be able to analyze specifically only the smallest grain sizes. To be able to do this, we cannot grind or pulverize the sample because this would make everything into the small clay-sized fraction that we want to. So what we have to do is we have to separate the sample along the different cleavage planes to then be able to extract only the size particles that we want to study. How is this done? So first off, the samples were coarsely crushed. This was done in a jaw crusher. After that, it was immersed into deionized water. This allowed for the water to penetrate into the pore spaces and along the cleavage planes of the different minerals. After this, the water was then flash frozen. This is a process called a deaggregation or disaggregation or jelly fractionation. This is freeze-induced fractionation. Finally, we dried and sieved the fractions down, keeping only the smallest 150 nanometer or micrometer fraction, keeping the smallest fraction, and then discarding of the larger than 150 micrometer fraction, or keeping it for further analyses. After this, we only are analyzing that smaller fraction, but we cannot sieve this portion down into reliable fractions. So we took on the centrifuge method. We did this by using different staged centrifugation in different speeds and different timing. First off, we started with our largest fraction, which was our A fraction. After the A fraction was submitted to 200 RPM over 3 minutes, the A fraction was removed. This was the largest fraction. After we continued this different centrifuge method, which started off with 200 RPM, then sped up quickly to 4,000. What this did is it separated out the supernatant fluid from that A fraction. So that was supernatant fluid was between the fractions of B and C, and then that was the D fraction, or between the fractions of A and B, and that was the D fraction. After it was centrifuged again, and then that supernatant fraction was removed again, and then that was the E fraction. So this centrifuge method split up the different size fractions into 4 generalized sizes. These are A, B, C, D, and E. The D and E are the supernatant removed liquid from the centrifuge fractions, and these are the smallest. These A, B, and C fractions were determined to be these different size fractions based on both qualitative and quantitative analysis. The D and E fractions then underwent dialysis. This allowed for the equilibrating of substances through a cellulose membrane. Therefore, only the colloids that were in the supernatant fluids would then be subjected only into the one side of the cellulose membrane. They would not have the ability to pass through this membrane, and therefore one fraction would remain strictly the colloid material. The material that passed through the cellulose membrane would be the ionic loads of the sample. Therefore, we can split the supernatant fluids of D and E into D-C and E-C, which are the colloid fractions, and the ionic loads, which are D-I and E-I. Therefore, in total, for each sample, we have 7 different size fractions. We have size A, B, C, then our colloid fractions, which are D-C, and then our ion fraction, which is D-I, and then followed by E-C and E-I. So these size fractions, what did we do with them? Well, we first off had to had to dissolve and digest these samples to be treated and tested by the triple quadruple ICP-MS. This is an extremely accurate ICP-MS with very, very high precision results. Second, we had to grain mount the sample, which is then analyzed by SEM and XRD. Our SEM. First of all, this main reason to use the SEM was to be able to understand the different size fractions. We did all of our analysis based on centrifuging, based on that the size fractions were perfectly circular and applied strictly to the laws of physics. Therefore, this was the idealized circumstance. Knowing that these different minerals are not perfectly circular, we must look at them under the microscope to be able to determine the exact size fractions. Therefore, we had to mount our A, B, C, D, and E fractions to be able to understand what grain sizes they were. Also, we could use the EDS detector, which is the energy dispersive spectrometer, on the SEM to be able to semi-qualitatively analyze the different minerals in the grain mount. Heavy minerals such as pyrite, arsenopyrite, and magnetite were found only in the largest fraction. Therefore, they were centrifuged out extremely early in the process. With our smallest fractions, including D and E, gradually having higher amounts of the smallest size fractions, primarily including the micas, including chlorite. Now looking at our SEM results. So we have our A, B, C, D, and E fractions. We can see that just based on the scale of the photos, we find that our largest fraction or the largest grain sizes are A, and our smallest grain fractions are in the E fractions. As you get more and more, as the magnification of the SEM increases more and more, the clarity of the photo becomes less. This is due to the very small size of the grains and then being scattered when the SEM would try to take a very specific and defined photo. This is due to not having enough material on the slide and it not being able to be stuck down to the slide to be able to get a perfect photo of the different grains. Although this is why it's considered semi-qualitatively analyzed. If it was extremely accurate, we'd only need to do SEM analysis and we'd be able to determine the results. Although this is not the case. So this is why it's considered quantitative. Next, we looked at our XRD results. So each of these grain-mounted samples were SEM'd first and then were taken to the XRD. The XRD allowed for further identification of the sheet silicates in these smaller size fractions. These included the micas and the clay minerals. With the XRD, the grain mounts were scanned a total of 4 times. This was following along with the USGS sample method of how to identify clay minerals. Firstly, the first treatment is air dried at room temperature. Therefore, nothing is done to the XRD slide. After this, they are saturated for 24 hours within ethylene glycol. This was done to allow for the clays to glycolate, which then we're able to identify with different peaks changes. After the samples were heated for 1 hour at 400 degrees, this allowed for the dehydration of specific minerals. And finally, they were heated for 1 hour at 550 degrees, and this is further dehydration of these clay minerals. This clay identification is a method proven by the USGS. In this flowchart, we can see that first off, we find our different peaks located at our different amount of angstroms. So in this example, we have a peak at around 29 angstroms and a peak around 14 angstroms. After our first treatment, we can find that we have a peak at that point. That peak then will undergo changes based on the conditions it's subjected to. So first off is treated with ethylene glycol. After ethylene glycol, there could be a change, there could not be, and then is subjected to a second type of treatment. This treatment is 400 degrees for at least half an hour, which we produced up to 1 hour of heating, and then finally heating to 550 degrees at least 1.5 hours, or at least half an hour, which we did 1 hour. So this was how we were able to determine which type of clay minerals were found within the XRD results. So this is an example of our clay minerals. This is for analysis of 19A. We're finding peaks at 14 angstroms, 10, and 7 angstroms. These are being interpreted as a chlorite sample. Second, we are now analyzing sample 28D. So we are finding peaks at 10 angstroms and 7 angstroms. These different peaks are interpreted as sepalite, palygorskite, and halosite. And finally, a sample 29A, peaks are at 10 angstroms and 7 angstroms. These peaks are interpreted as chlorite and mulmillerite, or illite vermiculite. So therefore, after running all of our samples, we found that there are numerous peaks at different d-spacings, including 14 angstroms, 12 angstroms, 10 angstroms, and 7 angstroms. The minerals identified at these peaks were chlorite, interstratified illite chlorite, interstratified illite mulmillerite, or illite vermiculite. Those were the primary clay minerals, although we also found minor amounts of secondary minerals or secondary clay minerals found in the samples, including these. Another analysis that we did is thermogravimetric analysis. This was done to identify the different rates at which the samples dehydrated and dehydroxylized. We know, and we can see by these different values, we're finding a generalized 2 dehydration events. First one occurring from 500 to 900 degrees, and the second one, the different dehydration events are occurring from 500 to 900 degrees, although standardly there are 2 distinct devolatilization events. The first one is occurring at 450 to 620 degrees, and secondly is from 600 to 770 degrees. Now going into the general basis of the understanding of this paper. So these different samples were all of the samples that were used in this situation were digested and analyzed using triple, quadruple ICP-MS. So very highly accurate ICP-MS. When we looked at the specific size fraction of gold, so the amount of gold within the size fraction A, B, C, or the size fraction in the different colloidal ions, we can compare it versus the amount of gold found in the whole rock fraction. So that's when we had all of the fractions, all of them still together in one whole rock. Therefore, we can find a different relationship between our whole rock gold content and our specific size fraction. This is one of the most important points in the paper, so I want to make sure it's understood. So therefore, when we arrange our A, B, C, D, and E fractions versus our whole rock fraction, we don't find an analysis. Although, when we look at the size fraction and compare it to the enrichment factor, is where we start getting a trend. So then comes in the question of enrichment factor. What is an enrichment factor? This enrichment factor is when we compare the difference between the specific size fraction compared to the whole rock gold. So when the whole specific size fraction is 10 times the amount of the whole rock gold content, then that would have an enrichment factor of 10. Therefore, we can look at the different size fractions and the enrichment factor, and we can see that most of them are hanging around the 1 level enrichment, which we would regularly assume would be. If gold was segregated to no specific mineral and it was only equally aligned with all the different size fractions, we would find we would have all of our samples lining up at a 1 enrichment factor. Although we're finding these outliers from the pack in our A and our D and our D fractions, as well as some of their B fractions, we're finding upwards of 100 times more enrichment in a specific size fraction when compared to the whole rock gold content. This is the question of why do we find this? In this situation, why do we find more gold content in a specific size fraction when compared to the whole rock gold content? So when we compare our whole rock gold, our gold enrichment factor plotted against whole rock gold, we find that only our D and our E fractions are having this negative correlation, where we're having a standard regular correlation, a straight line. When we're having more gold, we're having more enrichment, or it could be as we're having more gold, we're having near 1 enrichment. So there's no large correlations in our A, B, and C fraction. But in our D and E fraction, we are finding these correlations where when we're having more whole rock gold, we are having more enrichment. So when we're having less whole rock gold, we're having more enrichment, and when we're finding more whole rock gold, we're finding less enrichment. Remembering that these D and E fractions are only made out of the sheet silicates, due to centrifuge, all of the sulfides and all of the other standard gold-bearing minerals are removed. So how are we having gold located within our D and our E fractions if there are no minerals that should be hosting it? The next we look at our enrichment factor versus our chlorite. So we're finding we are having more gold enrichment. The enrichment factor is highest when there is a larger amount of chlorite. So we can see in all of our A, B, C, D, and E fractions, we're finding chlorite. Although when there is the highest amount of chlorite, specifically in our D fraction, we are finding a larger amount of gold enrichment. And these same charts were correlated with biotite as well as the other accessory minerals found in these samples, although no strong correlations were found. Although there is another positive correlation found within our D and our E fraction. These are positive correlations on the reverse of our last sample, which we saw negative correlations, but these are positive correlations. So as the more chlorite we are having, the higher the enrichment factor. So you're having a general formation forming like this and like this. So now discussing why are we finding these correlations and what does it actually mean. So we first need to look at our colloid and our ionic gold fractions. We know that our D and our E samples are both sulfide and oxide free, meaning they have no standard gold-bearing minerals. Therefore, how are we having gold found in these samples when there is only clay minerals? Our XRD showed presence of different euhedral anhydrite, halite, and sylvite. Therefore, there must have been a presence of sulfate or chlorine in the water, which could have enhanced the solubility of the golden liquid. And this is why we're finding these different minerals forming in these mounts. So remobilized gold. How does gold actually form? So in these types of deposits, we are finding in Archean deposits, gold is hosted primarily by pyrite and arsenopyrite. This gold was deposited 2.7 billion years ago, and as it's deposited in different epithermal systems or orogenic systems, we're finding that gold is relatively close to the surface and could be affected by meteoric groundwaters. We know that these meteoric groundwaters are affecting the system because this is why we have such a heavy amount of alteration. This alteration is depositing minerals alongside these hydrothermal fluids, which are retrograding the minerals back, or the minerals found within the sample lithology, back to lower grade minerals, including illite, palygorskite, and halloysite. The chlorite has appeared to have resisted the retrogradation process the most, and this is why we're finding chlorite in our petrography samples very, very heavily altered, but still remaining. So determining through our testing, we have found that first off, the proposition of a chemo absorbed metal or metallic cation, the idea that these metallic cations can chemically bond to a clay mineral has been proven. This is called chemo absorption. So what we are doing is we are taking a proposition of something that has been proven in a lab and relating it to the world. And we know that the primary site of gold was in the pyrite and arsenopyrite sulfides. It had been transported and weathered away by groundwater and hydrothermal interaction, and has been transported in ionic form. This ionic gold is unstable and wants to be absorbed by another mineral. Therefore, the minerals that are being transported alongside these hydrothermal alteration fluids can allow for adsorption of these gold ions. So these gold ions then are partially attached to the weathered chlorite found within the fluids. This ionic gold can also penetrate into the interlayer space of the retrograding silicates. So not only is it going on top of the very high surface area sheet silicates, but it can also penetrate physically into the interlayer of the tetrahedride and oxyhedral layers. So finally, we're looking at the colloid versus ionic size fractions. So we're finding that using partition coefficients, it can be calculated that 5 to 50 times more gold is present in the colloid fractions when compared to the ionic fractions. Therefore, this is taking the smallest size fraction and splitting it into the colloids and ions. And we are finding that the gold is more heavily associated with the colloids. Therefore, if we take this and try to relate it to the world, we find that the gold is more efficiently transported by the colloids, or the clay minerals that are found in the aqueous solution that is remobilizing the gold. Therefore, it wants to be a part of these different clay minerals, and it does not want to be separated into these ions, into these metallic ions. So conclusions, by looking at the different size fractions and the different analyses, we can determine that sheet silicates are effectively remobilized by groundwaters that follow the emplacement of the original gold. This remobilization takes the gold away from its primary site in the arsenopyrite and pyrite and can transport it to a secondary site, which is in colloidal sized chlorite. The partitioning of this gold was measured between clay nanoparticles and the host liquid and suggests that the is more efficiently transported by the colloids when compared to its ions. Finally, this is just looking at a conceptual model of how this could be used in the understanding of different mineral deposits. If we were looking at a situation where we are having this remobilization of gold, we would have different zones of colloidal mica enrichment. Therefore, as we're coming closer to the gold deposit, we're having a higher amount of zone of gold enrichment. While we're getting farther and farther away, we're getting less and less. So this could actually be used to determine the where a gold deposit is located. If we were to take drill holes and drill them down, we might not hit this actual gold enrichment zone or where the gold ore is. But it's possible that we could hit this zone of colloidal mica gold enrichment, and then we could use the hydrological flow to trace back this remobilization to where the actual high grade gold deposit is. This method still needs to be tested within the field, although using this paper, we have determined that these zones of mica enrichment can be determined, although we are unsure of how the hydrological flow and the history of the hydrological flow would affect these zones. Therefore, this needs to be tested in theory. Finally, I'd like to just thank the collaborators on this NSERC project. Firstly, I'd like to thank Greenstone Gold Mines and specifically Shannon Wally, as well as different logistical help from Andrew Timms. The field season was originally conducted in 2018, and this project was presented later in 2019. And it was funded through a grant given by NSERC in collaboration with Greenstone Gold Mines. Thank you very much.